Welcome to the deep dive. Today, we're going to be looking at Cassandra,
Oh, yeah.
a distributed storage system that handles massive amounts of data.
Right.
And you're probably thinking, okay, but what's in it for me?
Mm-hmm.
Well, you'll be surprised to know that Cassandra plays a role in something you probably use every day, Facebook.
Absolutely.
Our mission is to understand how it works,
Yeah.
especially how it manages to keep all that data safe and sound,
Right.
even when things go wrong. And the best part is we're using the research paper by Cassandra's creators as our guide.
That's right.
It's like getting a sneak peek behind the curtain at Facebook.
It is. It is. It's really fascinating to see how they solved some really tough engineering challenges back then.
Yeah.
To truly appreciate Cassandra's design,
Okay.
we need to understand the context. Think back to Facebook in the late 2000s.
Okay.
Hundreds of millions of users,
Right.
tens of thousands of servers,
Yeah.
and data growing exponentially.
I can't even imagine.
Traditional databases simply couldn't handle that kind of scale and complexity.
So it's like trying to cram a library into a shoebox.
Pretty much. They needed a system that could not only store vast amounts of data, but also cope with inevitable hardware failures. In distributed systems like this, failure isn't a question of if but when.
Right.
Cassandra was built to embrace that reality.
Okay, so let's dig into how Cassandra actually works. First up, the data model.
Mm-hmm.
Now, traditional databases typically organize data in rows and columns, right?
Exactly, yeah.
But Cassandra takes a different approach.
It does.
Tell me more about that.
Well, think of it more like a flexible filing system.
Okay.
With folders within folders.
Okay.
Cassandra utilizes super columns to create these complex data structure.
Yeah.
Perfect for storing data like your Facebook inbox search index.
Interesting.
Every word, every message ID is meticulously organized.
Wow.
So when you search for something, Cassandra can pinpoint it in a snap, even if it's from years ago.
So these super columns are like a super-powered filing system.
You got it.
But how does Cassandra manage to spread all that data across multiple servers?
Right.
That's where partitioning comes in, right?
It's like dividing that giant encyclopedia we talked about
Okay.
across multiple bookshelves.
I see.
But here's where it gets interesting. Cassandra uses a technique called consistent hashing to distribute the data. This ensures that no single server becomes a bottleneck or a single point of failure, even if a server goes down.
Oh, wow.
The system knows precisely where to find the information it needs.
So it's like having a backup plan for your backup plan.
Exactly.
Hmm.
Cassandra keeps multiple copies of your data spread across different servers and sometimes even different data centers.
Wow.
That means even if an entire data center goes offline,
Oh, my goodness.
your data is still safe and accessible?
That's reassuring to know. But hold on. How does it keep tabs on all these servers?
Right.
Especially when they're constantly joining and leaving the network.
Yeah.
I mean, it's a bit like a busy train station, isn't it?
You could say that.
Yeah.
Cassandra nodes use a gossip protocol to communicate with each other, sharing information about which nodes are active and which ones have failed. It's like a constant chatter that keeps everyone updated on the state of the cluster.
Gossip, huh? Sounds a bit like my social media feed. But gossip can be unreliable.
It can.
How does Cassandra separate actual failures from false alarms?
That's where the brilliance of its design comes in. Cassandra uses sophisticated statistical methods specifically, and accrual failure detector to analyze these gossip messages and filter out the noise. It's like having a super smart detective sifting through clues to identify real problems.
So it's not just blindly believing every rumor it hears.
Absolutely not. It's using statistical analysis to make informed decisions about which servers are truly down. This level of intelligence is crucial for maintaining a stable and a reliable system at Facebook scale.
Okay, so Cassandra's starting to sound like a pretty smart system.
It is.
But I'm curious, how easy is it to actually expand this system? What happens when Facebook needs to add more servers to handle even more data?
That's one of Cassandra's greatest strengths. Its ability to scale seamlessly. You can add new servers to the cluster, and it automatically rebalances the data without any downtime. Think of it like adding a new wing to a library without interrupting the flow of readers.
Seamless scaling. That's impressive. But let's dive a little deeper into how Cassandra actually stores all this data on each server. We know it uses both memory and disk, but how does that work in practice?
It's a clever combination of speed and reliability. When you write data to Cassandra, it first gets appended to a commit log, which is like a permanent record on disk. This ensures that even if the server crashes, the data can be recovered. It then gets updated in an in-memory data structure called a mem table for lightning-fast access.
So it's like taking notes on a whiteboard and then transferring them to a more permanent notebook later.
Exactly. The mem table is all about speed,
Okay.
while the commit log is all about durability. Eventually, the mem table gets full and needs to be flushed to disk, which is where a new file called an ssstable comes in.
Is stable? That sounds pretty technical. Can you break that down for me?
ssstable stands for sorted strings table.
Okay.
And it's basically a file on disk that contains the data from the mem table, neatly sorted by key. Over time, as more data is written, Cassandra creates multiple ssstables.
So we've got commit logs, mem tables, and now ssstables. It sounds like a well-organized, multi-layered system. But how does Cassandra keep track of all these files and make sure it can find the data we need quickly? I mean, it's starting to sound a bit like my overstuffed filing cabinet.
Don't worry, Cassandra is much more organized than your filing cabinet. It uses a combination of indexes and a clever technique called a Bloom filter to efficiently locate the data. The Bloom filter quickly tells Cassandra which stables might contain the data you're looking for, saving a lot of time and effort.
So it's like having a master index that tells you which drawer to look in before you even start rummaging through files.
Exactly. And to make things even more efficient, Cassandra periodically performs a process called compaction, where it merges multiple ssstables into a single larger one. This not only saves space, but also improves read performance because there are fewer files to search through.
Compaction, so it's like decluttering and reorganizing your digital filing cabinet every now and then.
That's right.
That makes sense. So far, Cassandra sounds pretty impressive.
It is.
But I'm guessing there were some real-world challenges the team had to overcome when they were building and deploying this system at Facebook. What were some of those?
Oh, there are definitely some hurdles along the way.
I bet.
One of the most interesting challenges involved migrating the existing inbox data from their old system, MySQL, to Cassandra. We're talking about 7 terabytes of data for over 100 million users.
Wow.
That's a massive undertaking.
That sounds like a logistical nightmare. How did they manage to move that much data without disrupting Facebook's service?
Well, they got creative.
How so?
They used a technique called MapReduce to pre-process the data in MySQL and then sent it directly to Cassandra in a streamlined format, bypassing a lot of the usual conversion overhead.
So it's like finding a shortcut through a database.
Exactly.
Yeah.
This clever solution demonstrates Cassandra's flexibility and its ability to adapt to real-world challenges. It's not a one-size-fits-all solution. It allows for creative problem solving.
Yeah.
But like any system, it has its trade-offs.
So no system is perfect.
That's right.
What are some of the things that Cassandra isn't so great at? What are its limitations?
One thing to keep in mind is that Cassandra is optimized for speed and scale, especially when it comes to writing data. However, it's not the ideal choice for applications that require complex transactions across multiple data items, like transferring money between bank accounts.
So it's not a replacement for traditional databases in every scenario.
Right. Traditional databases are better suited for those kinds of complex, multi-step operations where consistency is absolutely critical. Cassandra excels at handling massive volumes of single data items with incredible speed and resilience.
So it's all about choosing the right tool for the right job. It's like having a toolbox full of different options. Sometimes you need a hammer, sometimes you need a screwdriver.
Precisely. And understanding the strengths and weaknesses of each tool is key to building successful systems. In Cassandra's case, it's a powerhouse for applications where high availability and scalability are paramount, even if it means making some trade-offs in other areas.
Okay, so we've got a good grasp of Cassandra's strengths and its data model.
Yeah.
But how does it actually handle those inevitable server failures? We touched on replication, but how does it guarantee that the system stays up and running, even when things go wrong?
That's where the magic of failure detection and recovery comes in. Remember those gossip messages we talked about earlier?
Yeah.
Well, they play a crucial role in detecting when a server goes down.
So it's like a network of informants constantly reporting back on the status of each server.
Exactly. And once a failure is detected,
Okay.
Cassandra automatically kicks in its recovery mechanisms. The data that was stored on the failed server is re-replicated from the other copies,
Interesting.
ensuring that the system remains operational.
So it's like having a self-healing system where the remaining servers step up to fill the gap when one of their comrades falls.
Exactly. And this ability to gracefully handle failures is one of the key reasons why Cassandra is so popular for mission-critical applications. You don't want your entire system to crumble just because one server has a bad day, right?
Absolutely not. It's reassuring to know that Cassandra has these safeguards in place.
Yeah.
But let's get back to that concept of eventual consistency that you mentioned earlier. I have to admit, it's a bit of a head-scratcher for me. Can you explain it in a way that even I can understand?
Of course. Think of it like this. In a traditional database, every time you read data, you expect to get the absolute latest version. But in Cassandra, with its distributed nature and focus on availability, there might be a slight delay before all the copies of the data are perfectly synchronized.
So it's possible that two people looking at the same piece of data might see slightly different versions for a short period of time.
That's right. But the key here is eventual.
Oh, yeah.
Cassandra is designed to resolve these inconsistencies over time. So while there might be temporary discrepancies, the data will eventually converge to a consistent state.
So it's like waiting for the dust to settle after a minor earthquake.
That's a good analogy. It's important to remember that this eventual consistency is a deliberate design choice, a trade-off that allows Cassandra to achieve its remarkable speed and resilience.
So it's not a bug, it's a feature.
Exactly. It's a feature that makes Cassandra incredibly well-suited for applications where high availability and fault tolerance are paramount, even if it means sacrificing a bit of strict consistency in the short term.
All right, I think I'm starting to wrap my head around this eventual consistency thing. It's a different way of thinking about data, but it makes sense given Cassandra's goals. But I'm curious, how do developers actually work with this concept? Does it make their lives more difficult?
It definitely requires a shift in mindset, but there are well-established patterns and techniques for dealing with eventual consistency. For instance, developers can use conflict resolution strategies to handle situations where multiple updates to the same data item occur concurrently.
So it's like having a referee to decide which update wins when there's a disagreement.
Precisely. Cassandra offers several built-in mechanisms for conflict resolution, giving developers flexibility in how they manage potential inconsistencies.
So it's not just about accepting eventual consistency, it's about having the tools and strategies to manage it effectively.
Exactly, and that's a key part of what makes Cassandra such a powerful and versatile tool for building modern data-intensive applications. It provides a framework for handling the challenges of distributed data in a way that traditional databases simply can't match.
I have to say, Cassandra is turning out to be even more fascinating than I expected. Before we get too carried away, let's take a step back and remind ourselves why we're diving into this technology in the first place. We started by talking about Facebook and its need for a robust data storage solution. Can you give us a concrete example of how Cassandra is actually used at Facebook? What's a real-world application that we can all relate to?
Well, think about your Facebook inbox and the search feature. Remember those super columns we talk about?
Yeah.
They play a key role in making that search lightning fast. For each user, Facebook stores an index of all their messages in Cassandra. The user ID acts as the key, and the words in each message are stored as supercolumns.
Ah, so when I search for birthday party in my Facebook inbox, Cassandra sifts through all my messages and quickly pulls up only those that contain those keywords.
Exactly. And to make things even faster, Cassandra uses intelligent caching.
Okay.
When you click on the search bar,
Yeah.
it preloads your message index into memory.
Wow.
So when you type your search, the results are practically instantaneous.
It's like having a personal assistant who knows exactly what you're looking for before you even ask. That's pretty slick.
It is, and this is all happening on a massive scale. The Facebook inbox search system stores over 50 terabytes of data on a cluster of 150 servers spread across multiple data centers.
That's a lot of messages. So we've got speed, we've got scale, and we've got reliability. Cassandra sounds like a pretty formidable system, but I'm curious, are there any other ways that Facebook utilizes Cassandra beyond just inbox search?
Oh, absolutely. Cassandra powers many other Facebook services, including their messaging platform, their photo storage system,
Yeah.
and even their internal analytics tools. It's a testament to Cassandra's versatility and its ability to handle a wide range of data storage needs.
So Cassandra is like a Swiss Army knife for data storage at Facebook.
That's a great way to put it. It's a flexible and powerful tool that can be adapted to many different use cases.
Well, it sounds like we've covered a lot of ground in this deep dive into Cassandra.
We have.
We've explored its origins, its key features, its strengths and weaknesses, and even seen how it's used in real-world applications, like Facebook inbox search.
But before we move on, I want to leave you with a question to ponder. We've focused on Facebook today, but what other applications could benefit from Cassandra's unique capabilities? What other industries or domains could leverage its power and flexibility?
That's a great question to consider as we move forward in our exploration of Cassandra. Think beyond social media. What about scientific research, financial transactions, or even managing vast amounts of sensor data from the Internet of Things.
The possibilities are truly endless. And that's what makes the world of distributed systems and data management so fascinating. There's always something new to discover, always a new challenge to tackle.
Absolutely. And as we continue our deep dive into Cassandra, we'll explore even more of these fascinating applications and delve deeper into the intricacies of this remarkable technology.
So stay tuned and get ready for part 2 of our deep dive into the world of Cassandra. It's fascinating how the challenges Facebook faced back then are increasingly relevant today. It's not just social media giants grappling with massive data sets anymore.
That's a great point. Think about all the data generated by sensors, IoT devices, scientific research, financial markets. It's mind-boggling. It's like the whole world is becoming a giant data factory.
Exactly. And that's why understanding the principles behind systems like Cassandra is so important. Even if you're not building the next Facebook, it gives you a framework for thinking about data storage and management at scale.
Okay, so let's get back to the nuts and bolts of how Cassandra works. We've talked about partitioning and replication, but there's another crucial piece of the puzzle that's essential for its scalability and fault tolerance, how it handles new nodes joining the cluster.
Right. Imagine a new server wants to join the Cassandra party. It needs to figure out where it fits in the grand scheme of things. It can't just barge in and start grabbing data randomly.
Right. There needs to be some sort of protocol, an onboarding process,
Yeah.
like a guest arriving at a well-organized dinner party.
Precisely. That's where the concept of bootstrapping comes in. When a new node joins the cluster, it picks a random token representing its position on the ring. Remember that consistent hashing we talked about?
Ah, yes, the metaphorical bookshelves arranged in a circle.
Exactly. So the new node announces its token to the cluster, and the existing nodes figure out which data ranges the new node should be responsible for. Then they start streaming that data over to the newcomer.
It's like the other servers are welcoming the new node and saying, here's your share of the work, now let's keep this party going.
Exactly. And the beauty of this process is that it all happens automatically and without any interruption to the service. The data just seamlessly redistributes itself to accommodate the new node. This dynamic scaling is crucial for handling ever-growing data demands.
It sounds like a well-choreographed dance where the servers constantly adjust their positions and share the workload to keep the data flowing smoothly.
A very apt analogy. But it's not just about adding new nodes. Cassandra also needs to handle nodes leaving the cluster gracefully, whether due to planned maintenance or unexpected failures.
Right, we can't have servers dropping out of the party and taking their data with them. That would be disastrous.
Indeed. When a node leaves, the other nodes detect its absence through that gossiping mechanism we discussed earlier. They then redistribute the data that was stored on the departed node among the remaining nodes.
This system of joining and leaving the cluster sounds remarkably efficient. It seems like Cassandra is designed to adapt to change on the fly without missing a beat.
That's precisely the goal. This ability to dynamically scale up and down is what makes Cassandra so well suited for handling the unpredictable demands of modern applications.
So we've covered the basics of how Cassandra distributes data across multiple servers and handles failures. But let's zoom in a bit and talk about how it actually stores data on each individual server.
Okay.
Remember we mentioned that Cassandra uses both memory and disk storage for performance and durability?
Yes.
Like taking notes on a whiteboard for quick access and then transferring them to a more permanent notebook for safekeeping.
Well, let's break down how that works in practice. When you write data to Cassandra, it first gets appended to a commit log, which is a special file on disk for persistence.
So it's like a logbook where every data change is recorded in chronological order, providing a complete history.
Exactly. This commit log is vital for durability because even if the server crashes, the data in the commit log can be replayed to recover any lost information. It's like having a safety net for your data.
A safety net is always a good thing, especially when dealing with something as important as data.
Absolutely. Once the data is safely written to the commit log, it's also updated in an in-memory data structure called a memtable. This is where the data resides for rapid access.
So it's like having a temporary, easily accessible copy of the data readily available for quick retrieval.
Exactly. But of course, we can't keep all data in memory forever. Eventually, the memtable gets full and its contents need to be flushed to disk for long-term storage.
Right. That makes sense.
Yeah.
So what happens when the memtable reaches its limit?
When the memtable fills up, Cassandra creates a new file on disk called an SS table, which stands for Sorted Strings Table. This SS table contains all the data from the memtable organized by key.
So it's like taking all those quick notes from the whiteboard and transferring them to a neatly organized file folder for long-term storage.
A very apt analogy. And over time, as more and more data is written to Cassandra, It creates multiple SS stables on disk. But this raises a question. How do we find the data we need amongst all these different files?
That's a great point. It'll be a nightmare to search through countless files every time we need to access a piece of data.
Exactly. That's where Cassandra's clever indexing and compaction processes come in. Each SS stable has an index that maps keys to their locations within the file. This allows Cassandra to quickly jump to the right spot on disk without having to scan the entire file.
So it's like having a table of contents for each file folder, making it easy to find what you're looking for.
Precisely. And to make things even more efficient, Cassandra also maintains a global index called a Bloom filter. The Bloom filter quickly tells Cassandra which SS stables might contain a given key, avoiding unnecessary disk reads and speeding up data retrieval even further.
It's like having a master index that tells you which file cabinet to look in before you even open a drawer.
A perfect analogy. And to keep things tidy and efficient, Cassandra periodically performs a process called compaction. During compaction, it merges multiple SS stables into a single, larger SS stable.
It's like taking all those separate file folders and consolidating them into a bigger, more organized file cabinet.
Exactly. This compaction process not only reduces storage space, but also improves read performance because there are fewer files to search through.
So it's a win-win situation.
Yeah.
Less clutter and faster access to the data.
Indeed. And this intricate interplay of commit logs, mem tables, SS stables, indexes, and compaction is what allows Cassandra to store and retrieve vast amounts of data with remarkable speed and efficiency.
It truly is a well-oiled machine with all these different parts working in harmony. It's impressive how much thought and engineering went into creating such a robust and efficient system.
It is a testament to the ingenuity of the engineers who designed Cassandra. They anticipated the challenges of operating at Facebook scale and developed innovative solutions that have since become industry standards.
Okay, so we've delved into the inner workings of Cassandra, from how it distributes data across servers to how it stores data on individual machines. But before we wrap up this part of our deep dive, I want to touch on one more crucial aspect of Cassandra's design: its approach to consistency.
Ah, yes, consistency. This is a fundamental concept in distributed systems and one that often differentiates Cassandra from traditional databases.
You mentioned earlier that Cassandra prioritizes availability and partition tolerance, even at the expense of strong consistency. Can you unpack that a bit for me? What exactly does that mean in practical terms?
Certainly. In a traditional database, you expect every read operation to return the absolute latest value that was written. Consistency is paramount. But in a distributed system like Cassandra, where nodes can fail and networks can partition, achieving that level of strict consistency can be challenging and can come at the cost of availability.
So it's a trade-off. You can have perfect consistency, or you can have high availability, but you can't always have both at the same time.
Precisely, Cassandra chooses to prioritize availability and partition tolerance, which means that there might be temporary inconsistencies in the data, especially during network outages or when nodes are failing and recovering.
So it's possible that two people reading the same data at slightly different times might get slightly different results.
That's right. But the key here is eventual. Cassandra is designed to resolve these inconsistencies over time, so the data will eventually converge to a consistent state.
So it's like waiting for the ripples in a pond to settle after a stone is thrown in. Eventually, the surface will be smooth again.
That's a good way to visualize it. This concept of eventual consistency is a core principle of Cassandra's design and one that sets it apart from traditional databases. It's a trade-off that allows for incredible speed, scalability, and resilience, but it's essential to understand the implications.
So it's not a silver bullet for every data storage need. It's about choosing the right tool for the job based on the specific requirements of the application.
Exactly. And that's what makes the world of distributed systems so fascinating. There's a wide spectrum of approaches and technologies, and the key is to understand the trade-offs and choose the solution that best aligns with your goals.
Well, this deep dive into Cassandra has been truly enlightening. We've covered so much ground, from the basics of its architecture to the intricacies of its data storage and consistency models. It's clear that Cassandra is a powerful and sophisticated system, and I'm eager to explore more of its capabilities in the part 3 of our deep dive. It's amazing how Cassandra handles failures so gracefully.
Right.
It's not just about detecting when a server goes down.
No.
It's about doing it intelligently and preventing those false alarms.
Exactly. Cassandra uses sophisticated statistical analysis of the gossip messages between nodes.
Right.
It's like having a seasoned detective, piecing together clues to determine the true state of the cluster. This helps prevent false alarms and ensures that the system only reacts to genuine failures.
And speaking of being proactive, we also touch on the importance of monitoring. Cassandra doesn't just rely on reactive measures. It's deeply integrated with monitoring tools like Ganglia, which provides a real-time view of the system's health.
Right, right. This allows operators to spot potential issues early on and take corrective action before they snowball into major problems. It's like having a team of doctors continuously monitoring a patient's vital signs.
So it's not just about building a robust system.
No.
It's also about having the tools and processes in place to maintain its health and stability over the long haul.
Absolutely. And that's a valuable lesson for anyone working with complex systems,
Yeah?
whether it's in software engineering, healthcare, or any other field. Proactive monitoring and early detection are crucial for preventing catastrophic failures.
Okay, so we've covered a lot of technical ground,
We have.
but I want to circle back to that concept of eventual consistency that we've been discussing. It's one of the most fundamental aspects of Cassandra's design, and I think it's worth revisiting to make sure we fully grasp its implications.
Yeah, it's definitely a paradigm shift for those accustomed to working with traditional databases where consistency is king. Eventual consistency requires a different way of thinking about data and how it's accessed.
Right. It's a bit like adjusting to a new set of rules in a game. You need to understand how the pieces move differently.
Exactly. In a traditional database,
Yeah.
you expect every read operation to return the absolute latest value. But in Cassandra, that's not always guaranteed.
Because the data might be temporarily inconsistent across different nodes in the cluster.
Precisely. And that's where the concept of tunable consistency comes in. Cassandra allows developers to specify the level of consistency they need for a particular operation. It's about finding the right balance between consistency, availability, and performance based on the needs of the application.
So it's like having a dial that you can adjust depending on the situation. Sometimes you need absolute consistency, even if it means waiting a bit longer, and sometimes you can tolerate a bit of inconsistency if it means faster response times.
That's a great analogy. This flexibility is what makes Cassandra so versatile. It can be adapted to a wide range of applications,
Wow.
from those that demand strict consistency to those that can handle a more relaxed approach.
This tunable consistency sounds powerful, but I imagine it also adds complexity for developers.
It does.
They need to understand the trade-offs and make informed decisions about the right consistency level for each operation.
You're absolutely right. It does require careful consideration. But the good news is that there are well-established patterns and techniques for dealing with eventual consistency. For example, developers can use conflict resolution strategies to handle situations where multiple writes to the same data occur concurrently.
So it's like having a set of rules for resolving disputes when multiple people try to update the same document at the same time.
Exactly. Cassandra provides several built-in conflict resolution mechanisms, such as last write wins or merge, allowing developers to specify how conflicting updates should be handled. It's about having the tools and strategies to manage eventual consistency effectively.
It seems like the key takeaway here is that eventual consistency isn't just something you accept passively.
Yeah.
It's something you actively manage and design around.
Precisely. And that's part of what makes Cassandra such a compelling technology. It provides a framework for embracing the challenges of distributed data and building applications that are both scalable and resilient.
Well, I have to say, this deep dive into Cassandra has been a real eye-opener. It's a fascinating technology that challenges conventional thinking about data storage and management. We've explored its architecture, its strengths and weaknesses, its unique approach to consistency, and even seen how it powers critical services at Facebook. What an amazing system.
It's been a journey into the heart of a technology that's shaping the way we handle data in the modern world.
And as we wrap up, I want to leave our listeners with a final thought. We've focused on the technical details of Cassandra,
We have.
but the real magic lies in its ability to solve real-world problems. It's about building systems that can handle the ever-growing flood of data
Right.
and making sure those systems are reliable, scalable, and performant.
As you continue to explore the world of data management and distributed systems, remember the lessons we've learned from Cassandra and embrace failure as an inevitability, prioritize availability, and don't be afraid to challenge the status quo.
Because in a world where data is increasingly valuable, the ability to manage it effectively is a superpower. And tools like Cassandra empower us to build truly remarkable things.
So keep learning, keep experimenting, and keep pushing the boundaries of what's possible. Who knows, maybe you'll be the one designing the next generation of data storage systems that will power the world of tomorrow.
That's a great note to end on. Thanks for joining us on this deep dive into the world of Cassandra.